Good afternoon, class. So, for this lecture, we are aiming to complete section 2.3a and 2.3b. So, that's what we've got on the plate for today. Um, yes, as you may notice, I am indeed wearing the same shirt you saw in the last video. That would be because I was making this video on the same day. So, the more you know, I guess. At any rate, 2.3a is where we are starting today. 2.3a. And we want to cover some new vocabulary building off this idea of what is a derivative, what is slope, what does it mean for a derivative to exist, so on and so forth. That's what we're aiming for. So let's recap. We already know that we have this definition. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And so we say the derivative is this value, the resulting value of this limit, if the limit exists. Now recall from, I believe it was 2.1, where we were discussing what are limits, what does it mean for a limit to exist. Those things we discussed there are going to come up again here. In order for a derivative to exist, the limit must also exist, and vice versa. If the limit doesn't exist, then the derivative doesn't exist. So this is going to be important terminology based off of what we learned in section 2.1. So let's keep going. So based on this, if f prime of x exists, then we say the function f is differentiable. Differentiable. And all that means is we can take the derivative of it. Furthermore, and these first few things are just covering some basic vocabulary words that you're not going to be tested on, but as we talk and we go into other future lectures and I use some of these words, it's important to know what they mean, or at the very least that you understand what I mean by them when I use them. So this next part, so the process of finding the formula f prime of x is called differentiating. It's a verb. It means to take the derivative of something, differentiating. Furthermore, this process is called differentiation. Oops, my marker is running out of ink. So again, I mean, these words are not a big deal. I'm not expecting you to memorize them. The whole point of this is just to, what are these words? What do they mean in case you haven't heard them before? And what do I mean by them when I use them? So derivatives are slopes. Differentiable means you can find the derivative. Differentiating, that means I'm taking the derivative, I'm finding the derivative, I'm in the process of finding the derivative, and this entire process is called differentiation. Okay, so let's keep moving forward then. So we've talked about what it means to be differentiable, what it means to find the derivative, but let's discuss when something is not differentiable. So, a function f is not differentiable if any of the following happen. So the first case, if f of x is discontinuous at x equals some a in the value, or in the domain. What is discontinuous? Well, that's another vocabulary word we'll get into here in a moment. 2, a function f is not differentiable if the graph of f has a sharp corner. Well, what is a sharp corner? What do I mean by a sharp corner? Again, that's something we'll touch on in just a moment, but let me cover our third case and then we'll talk about it. Or third, the tangent line, remember we discussed what a tangent line is in the previous section, at x equals a is a vertical line. Now, what would that mean? Well, if we had a tangent line that was a vertical line, then it would be going straight up and down. In other words, the slope or steepness of that line would be positive infinity. That's infinitely steep compared to like something with a slope of 1, for instance. So this infinite steepness, that would mean the slope is infinity, or in other words, the first derivative is infinity, or in other words, the limit is infinity. But, as we discussed in the previous sections, when the limit equals positive infinity, even if it's agreed on from the left and right side, we consider that a limit to not exist then. In that case, we consider that the derivative does not exist in that case because the limit does not exist. And so it is not differentiable when the tangent line at that point is a vertical line. So those are 3 cases where f is not differentiable. But now let's take a moment and talk about what do I mean by discontinuous. So discontinuous, or discontinuity, this occurs any time that you have your graph drawn and you pick up your pencil while you're drawing it. For example, if I have a function and it's doing something funky, maybe it stops right there, and then maybe it picks up again up there and then goes on its merry way. In this example, my function is discontinuous. In other words, it's not fully connected. If you can draw your graph without picking up your pencil at all, then that's how you know that you're dealing with a continuous function, because each point is connected to the next point continuously. However, in this case, it is discontinuous because when you get to this point here, you have to stop and then start from another point. So it is a discontinuous function. Other examples of discontinuity, because this is an example where from the left side, the limit is coming to this point, but from the right side, it's going to a completely different point. So the left and right don't even agree. However, it's entirely possible to have an example where the limit and right do agree, they do come to the same point together, but the function is still discontinuous. For example, maybe I got my function, it's doing something like this, then I've got an open circle here. So it's not filled in, but then maybe the function continues from that exact same point and keeps going. And then at this point, let's say x equals 3, maybe f is actually supposed to be this point floating up here in the above the function. In this case, the function is also discontinuous. Why is that? Well, even though from the left and from the right, the function does meet at this open circle, because that circle is not filled in and you actually have to fill in another point, you have to pick up your pencil and put your pencil down somewhere else. It is not a continuous function, and so it is discontinuous. This is another example where the derivative would not exist at this point. So there you have it. Anytime you're dealing with a function that has discontinuity, the derivative does not exist at a point of discontinuity. So keep that in mind. That's something important you're going to want to remember. So that's discontinuity. Now, the next point was f is not differentiable when it has a sharp corner. Well, what's a sharp corner? Well, probably the most popular example would be the absolute value function. F of x is equal to the absolute value of x. Or in other words, we can break this up into a piecewise function for positive and negative numbers. If we're looking at the positive x's, or when it's 0, then it's just the x line. And if we're talking about negative numbers, well, we throw on an extra negative to make it positive again. So then graphically, from the left, we have this negative x line. And then from the right, we have this positive x line. So this graph can be drawn without picking up my marker, picking up your pencil. It's completely continuous. So this function is not discontinuous, but you notice here at x equals 0, we have this sharp corner. We're going down, we're going down, we're going down. We got a slope of -1, and then suddenly we turn. And then our slope is +1 going in this other direction. This is what I mean by a sharp corner. Now, why is it discontinuous here? Well, think about it. If I try to take the derivative, then from the left side, I have this y equals -x line. Well, we already know that for a line that's of the form y equals mx plus b, m is our slope. So in this case, this line on the left side has a constant slope of -1. Whereas vice versa on the right side, it has a constant slope of 1. So as I approach 0 from the left, and if I'm trying to estimate what the derivative is at 0, or what is the slope at 0, from the left side, the line says it's -1, -1, -1, -1, -1. As close as I get to 0, so long as I'm to the left of it, I'm always on this line that says the slope is -1. So from the left-hand side, or the left-hand limit, the slope, the derivative, is -1. Whereas from the right side, the slope is 1 for the right-hand limit. The left-hand limit and the right-hand limit do not agree. They're giving you two different answers. And so the limit at this point, the slope at this point, does not exist. And so it is not differentiable, and the derivative does not exist. So this is what I mean by a sharp point. Another good example to keep in mind. You will sometimes see other functions. Maybe you've got something that looks jagged all the way down. And this marker is dying on me. Let me see if I can fill it in. Yeah. It's jagged all the way. In this case, we have a lot of points where we have sharp corners and a derivative does not exist. So you want to keep your eye out for these kind of things, and just be mindful that at these points where we have these sharp corners, the derivative does not exist. All right, so let's see. Not differentiable, we've covered those three cases. All right, let's keep going then. Okay, so let's see. Not differentiable. Right. So we've discussed what it means to be discontinuous, but while we're at it, we want to go ahead and give a formal definition for continuity. What is continuity? So continuity, so we say f, a function, is continuous at a point x equals a if the limit from the right-hand side, so as x approaches a from the left of f of x, equals f of a, and the limit as x approaches a from the right for f of x also equals f of a. If this is true, then we say the function is continuous at that point. So what does that really mean in plain English? What we're saying is, for any point you pick in the domain, if as you approach a point from the left and as you approach that point from the right, if the limits meet at the same point, but not only do they meet at the same point, but they meet at the point the function is labeled, then we say it's continuous. So this definition is really good, especially for the example where we've got a graph and open circle, and then the graph continues and connects at the same point, but we fill in up here. This is not continuous because the definition of continuity says not only do the left and right hand limits have to agree on the same point, but they have to equal what the function actually is. At this point for a, whatever that is, f of a is this dot up here. The left hand and the right hand limits do not equal that dot. They don't approach it. This definition includes this kind of case and says that they have to meet at whatever the point is for f of a. So for any of these other examples where it's continuous, if I pick a point, this is f of a, and from the left and right hand side, they meet there. And so we're golden, and we call that continuous. So this is the definition of continuity. If you're ever trying to prove that a function is continuous at a point, this is the way you want to do it. You're going to take the limit from the left-hand side, show that it equals f of a. Do the same for the right-hand limit, show that it also equals f of a, and then you're done. You've proven that the function is then continuous at that point. So that may be a nifty trick for any questions if you're asked if it's continuous at a point or not. So keep that in mind. Right. So we've covered not differentiable. What does it mean to be not differentiable? Discontinuity, sharp corners, continuity. Okay, so now we're ready to talk about some derivative shortcuts. Some rules we can use to take the derivative faster, which is going to be very useful to us as we move on to more complicated equations. So I'm going to go ahead and, erase this. And yeah, I'll go ahead and erase all of it. I'll leave the derivative here. We might want that later. All right. So we've got some tricks, some rules, some tips and tricks for how to take derivatives quickly without having to use this long and drawn out limit equation, because this can honestly get quite tedious after a while. But using some of these tricks we're going to talk about, it's going to make our life much easier. So some rules slash tips slash tricks. So trick number one, and really we touched on this in the last section, we just didn't fully describe that's going to be true all the time. Anytime you have, so given a constant number, a constant real number c, if f of x equals c, then the derivative f prime of x is going to equal 0. Now, why is this true? Well, think back to the example we had before where f of x equals -2. In this case, we had the horizontal line at y equals -2. And we talked about how the steepness of a flat line like this is 0. And this is going to be true for any horizontal line. It's flat, and so the steepness is 0, the slope is 0. And so anytime you have a function that's equal to a constant, regardless of what that constant is, it's going to be a flat line, and so your derivative is going to be 0. Well, okay, not such a big deal. We kind of already knew that, so maybe that's not so fancy. Doesn't really help us out that much. Well, let's keep going then. The next trick, and again, this may be another one that you may have already thought about and have come to grips with, but consider the case given m and b are constants, if f of x equals mx plus b, then f prime of x is equal to m. Now, why is that true? Well, think back. Mx plus b, what does that look like? That is our point-slope form equation for a line. Y equals mx plus b. And remember that when we wrote this equation back in Algebra 1 or Algebra 2 or whenever you had that class, m is your slope. And in the same sense, your first derivative, which we've discussed, is your slope. It's not a coincidence that we use the same word there. Slope and derivative are the same thing, and so m is also our derivative here. But if you're not quite sold on that, well, we can actually prove it using our limit definition for the derivative. So let's try it out. So here's our f of x, and we want to find f prime. So this is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And just like before, I'm just going to take what's in the inside and plug it into my function. So I'm going to have m times, excuse me, we're going to have m times, in parentheses, x plus h plus b minus f of x. And remember to distribute that negative. So minus mx minus b, all divided by h. Now when we do that, we're going to distribute the m up here and then subtract out our like terms. So we've got the limit as h goes to 0 of mx plus mh plus b minus mx minus b. Now note here that we've got a positive mx and a negative mx, so they cancel. We've got a positive b and a negative b, so they cancel. And all we have left is the limit as h goes to 0 of mh divided by h. Well, the h's divide out, and we have the limit as h goes to 0 of m, which is just m. And there you have it. So for any time we have a function that is just a regular old line, no powers, nothing's fancy about it, just mx plus b in this format, then the derivative is always going to be that m, whatever the slope is there. So a nifty trick, something worth remembering. It's going to save yourself the time of working through the steps of finding the derivative, but definitely worth remembering to find your derivatives there. All right. So, and again, you may have also already known that because, okay, point slope form equation of the line, m is slope, slope is the derivative, obviously m is the derivative. Okay, so maybe you didn't learn anything from that. That's all right. This next trick will definitely be something new. So for our third tips and tricks we'd like to talk about here. So given a and b are, are constants, if f of x equals a times x to the b power, then the derivative f prime of x is equal to, now this is called the power rule, because when we have x to some power, and it could be any number, any real number b, then in order to take the derivative of this, the b comes down, and so we have a times b times x, and then the power decreases by 1 since we brought 1 down here. So b minus 1 times there. And this is true for any x to any power with any constant on it. And that's why this is called the power rule. This is a good rule. It's something you definitely want to remember. You're going to use this over and over again for pretty much the rest of the class. In terms of why it's true, in order to prove it using the limit definition for the derivative, we actually need some induction and a few other things in order to prove it, which is a little beyond the scope for this class. So I'm not really going to talk about why this is true. Just that, well, we can do some examples that kind of help prove it to ourselves, but it's not going to be a thorough proof. So consider it proof on light, or whatever you want to call it. At any rate, power rule, good stuff. You want to hold on to that. Yeah. So let's do some examples then. So the first thing I'd like to do is to show you the power rule in action, and then also kind of do it the other way using the limit definition to prove that you really do get the same answer. So let's consider, and I'll write the rule up here. If I have f of x, which is ax raised to the b power, then my claim is that f prime is abx raised to the b minus 1 power. This is the power rule. So if f of x equals x cubed, then according to this rule, f prime of x is 3x squared. The 3 came down as a coefficient, and the power decreased by 1, 3x squared. And that's it. One step and I'm done. There's the derivative. But in order to try to help prove it to yourselves that this makes sense, let's try it with the old method using our limit definition for the derivative. So according to this definition, f prime of x is equal to, is equal to the limit as h goes to 0 for f of x plus h. So I'm going to plug in x plus h to my function. So I've got x plus h cubed minus f of x. Well, that's just x cubed. So here's my x cubed divided by h. And this gets a little messy with the cubic here. But we know that if we square this guy, we're going to have x squared plus x times h is xh, but double it, so 2xh plus h squared. So that's to the second power. So we still want to multiply it by one more x plus h. And we still want to subtract our x cubed over here. Then we keep going. We can multiply this out, and we're going to have x cubed plus 2x squared h plus xh squared plus xh squared plus 2xh squared plus h cubed. And we still have a minus x cubed. So it gets a little bit messy here in the numbers here. But our x cubes, they subtract out. And we're left with 2x squared h plus 2x... No, that's the only one we have. 2x squared h plus xh squared plus xh squared. So we got two of those. 2xh squared. And then we've still got our other 2xh squared over here plus an h cubed. And we got the limit as h goes to 0. So we can go ahead and divide out our h's here. And we're taking out the limit as h goes to 0. Dividing in our denominator, we're going to have 2x squared plus 2x plus, no, that's 2xh there. So we've got 2x squared plus 2xh, because we lost one of them, plus 2xh plus h squared. Did I do that correctly? I feel like I'm missing something somewhere. Let me just double check myself real quick. I did mess up somewhere. X cubed plus 2x squared h plus xh squared plus another xh squared plus 2xh squared plus h cubed. So x cubed, 2x squared h plus a 2x h squared minus x cubed. Hold on. Let me pause this and figure out what went wrong. All right, and we're back. So yeah, the mistake I actually made up here was when I was factoring in this x plus h. For these middle terms, I should have had an xh squared plus an x squared h. But when I combine all those like terms, then I get a 3x squared h plus 3xh squared plus a 2xh squared Actually, yeah, that shouldn't be there at all. Because I combined terms over here. So yeah, 3x squared h plus 3xh squared plus h cubed. We divide out the h's here. And we get 3x squared plus 3xh plus h squared. And when we plug in h is 0 as h goes to 0, we're left with 3x squared. So long story short, you get the same derivative regardless of which method you use. Only this way, when you use the limit definition, it can get a lot messier, and as you saw, it's very easy to make a mistake and lose your footing. But you end up with the same answer either way, and so the power rule works. So that was the whole point of that demonstration, though it wasn't as great as it could have been, but that's all right. Of course, we'll address any questions that come up, and we'll very likely do more examples like that in the Q&A later today. So don't worry about it too much. We can talk about it more if any of that wasn't quite clicking. All right. Now, let's see. For the sake of time, I think we're going to go ahead and move into 2.3b. And we'll be able to cover some more last-minute examples there. All right, so 2.3b, we'd like to discuss here now. We've got two new rules we'd like to point out just to make derivatives that much easier. The first rule is called the constant times function rule. Constant times function rule. What does that mean? Well, it's exactly what it sounds like, really. If we have y is equal to some constant c times f of x, then we say y prime, which is the first derivative of y, or another notation just to introduce it because you're going to need it later, y prime, or the first derivative, we can also write as dy dx, which all that means is the derivative of y with respect to x. So nothing fancy. It means the same thing we've been doing. So dy dx is equal to the constant, we can just leave it alone, let it sit on the outside, times the derivative of f, which is f prime of x. Well, this is great. What this is telling us is that if I have a function, maybe f of x is equal to 2 times x squared plus 1, then my derivative, according to the constant rule, says I can just leave the 2 on the outside and then multiply it by the derivative of this inside part. Well, the derivative of x squared plus 1, well, the derivative of x squared by the power rule is just 2x. And the derivative of 1, well, it's a constant, so it's 0. And so we have 4x for our final answer, which we would have gotten anyways if we chose to distribute the 2. Then by the power rule, 2x squared, the derivative of that is just 4x. You get the same thing either way, but the point being is that anytime you're dealing with constants outside of some other function, you can leave it on the outside and just take the derivatives you normally would, and then multiply it by the constant again. So, nifty little rule. It'll be more useful later. The second rule that we'd like to discuss in this section, which I actually accidentally used here, but you'll see why or how I used it in a moment. The second rule is called the sum and difference rule. And now all this says is if y is equal to some function plus or minus, it doesn't matter, some other function, some other differentiable function, then y prime, which is equal to dy dx, is equal to f prime plus or minus g prime. In other words, when you see a plus or minus between two functions and you're trying to take the derivative, you can distribute your derivative over the plus or minus and just completely ignore the plus or minus. Just remember to keep it there in the middle. That was the same thing I did up here when I was taking this derivative of the inside part. When I took the derivative of x squared plus 1, I went ahead and separated it based on this plus sign in the middle, and just ignored the plus sign for the moment and just took the derivative of each separately. The derivative of x squared was 2x, and the derivative of 1 was 0, so I didn't have to write anything there. So if I had written it all out, then I'd have the plus 0 here in the parentheses, which still got me to the same answer. So I ended up using the sum and difference rule when I took this derivative. Alright, so that's great. We've got 2 new rules to add on to those tricks we just learned in the previous section for 2.3a. Now we'd like to do a couple examples putting it all together. So for this example, let's look at, let's see, which one do we want to look at? Yeah, let's do this one. So f of x is equal to negative 2x squared plus 6 over 5 plus 5x to the 4th plus 6x to the 3rd. Now, we've got these plus signs separating all these different stuff, so by the sum and difference rule, I can just take the derivative of each part individually and then add them all back together again. So that's what we're going to do here. So f prime of x is equal to, so starting with this first guy, we'll use the product rule. Negative 2 times 2 is negative 4. Power decreases by 1, so it's x to the first power, plus the derivative of 6/5, or I'm sorry, yeah, 6/5, 6 over 5. That's a constant, and the derivative of the constant is 0. So we keep going. We bring the 1/4 down, so we have 5 times a fourth, or in other words, 5 divided by 4. The power decreases by 1. So 1/4 minus 1 is a negative 3/4 power. As nasty as that looks, that's a perfectly fine answer. And then for the last part, 6 times 3, that's 18. Power decreases by 1, x squared. And there we have it, negative 4x plus 5/4 times x to the negative 3/4 power plus 18 x squared. And while that might not be the most pretty looking answer, for this class, and especially as we start getting into derivatives, this is a perfectly fine answer. So don't sweat over the details of how to simplify or how to make your answer look better. Oftentimes, what you come up with for your answer here isn't going to look great, and that's okay. So don't worry about it too much. Let's see. And then, yeah, this was this last example I wanted to do real quick. So when you're working through your practice questions and your certified quiz, you're going to encounter some questions that ask you to calculate the tangent line. So what do I mean by that? Well, I'm going to read off one of these questions and just write it on the board as I go. So here we have given f of x equals x cubed plus 2x minus 4 at x equals -1, find the tangent line. So what is the tangent line? Well, remember, let's just break it down first. Line, in order to find a line, we're talking about y equals mx plus b. So what do we need for that? Well, 1, we need a slope, and 2, we need a xy coordinate. Well, we're given -1, so if I plug that in for x, then I'm going to get -1 cubed, it's -1, -1 times 2, that's a -2, minus 4, 1 plus 2 plus 4, that's going to give me -7. All right, so there's half the battle. I've got a coordinate now, -1, -7. I still need to find a slope. But what is slope? That comes from the first derivative. So I'll do my power rule. 3x squared plus derivative of 2x. So 1 comes down, 1 times 2 is 2. Power decreases by 1, 1 minus 1 is 0. But x to the 0 power is just 1. So there's no x here, it's just 2. So now I plug in my -1 for x, and I'm going to get -1 squared is 1, times 3 is 3, plus 2 is 5. There's my slope. And now all I do is plug it into the point slope form. Y minus y1 is equal to m times x minus x1. So y plus 7 is equal to m times x plus 1. Or in other words, m is 5 here. M is 5. Or in other words, when I distribute 5x plus 5 minus 7, y is equal to 5x minus 2. And there you have it. There is the tangent line at x equals -1 on this curve. And that's it. That's very likely a question you're going to see, and that's a question you should definitely know how to do. So I may have ran through that a little bit quickly, but I mean, you can rewind, rewatch this last part of the video. You can see my lecture notes, and of course, we can talk about it during the Q&A. So that is everything for this lecture. Of course, let me know if you have any questions, email me with any problems, concerns, what have you, and we'll talk about it. So without a further ado, I wish you the best of luck. All right.